For today's Teichmüller theory seminar, we have the pleasure of welcoming Tengren Zhang from Caltech, who's going to tell us about the Goldman symplectic form on the PSLV Hitchin component.
Thank you, and thank you for the invitation to speak here today. I'm very happy to be here. Okay, so today I'll be telling you about some recent joint work with Anna Vinha and Jasun about the Goldman symplectic form of the PSLV Hitchin component. Okay, so let me begin by explaining to you what is the PSLV Hitchin component. Okay, you guys should feel free to stop me whenever there's something that's not clear, okay? So, for the rest of today, I'm going to let S be a closed, connected, oriented surface. Of genus at least 2. Okay, it's the negative order characteristic. And I'm going to denote the fundamental group of S by gamma. Okay? And I also let V be an n-dimensional real vector space. Alright? And then in this setting, you can talk about the Teichmüller space of S. Okay, if you've never seen this before, you should think of this, or in this talk at least, you can think of this as the deformation space of hyperbolic structures. On S. Okay? So this is all the essentially different ways to equip your naked topological surface with a hyperbolic metric. Alright? Now you can think of this space in a different way, in a more representation theoretic way. Then this is the set of discrete and faithful representations. So the representation is just a group homomorphism, right? From gamma to the group of orientation preserving isometries of the upper half plane, that's PSL2R. And I consider these representations up to conjugation by the isometries of H2, is PGL2R. Okay? Now the advantage of thinking of Teichmüller space, which is kind of a geometric object, from this representation theoretic point of view is that it meets a natural generalization, which is the PSLV Hitchin component. Okay? So to define these guys formally, I need to recall this fact from representation theory. There exists a unique, up to conjugation, okay, irreducible representation, which I'll denote by iota, from PSL2R into PSLV. Okay, and so this is usually people describe this via the Veronese embedding. Okay, but if you've never seen this before, that's okay. Okay, you should just think of this as some canonical way to put PSL2R into PSLV. Okay, and this gives you a way to embed the Teichmüller space of S into the space of homomorphisms from gamma to PSLV, consider up to conjugation by PGLV. Okay, yeah, I forgot. So do people know what PSLV, PGLV are? Okay, these are just, okay, so SLV is the set of endomorphisms from the vector space to itself that have determinant 1. And then if I consider these matrices up to scaling, then that's called PSLV. Okay, and PGLV is just a set of endomorphisms, invertible matrices, endomorphisms from V to itself, and you consider up to scaling, that's PGLV. Okay, so these are just two very classically studied E groups. Okay, so what is this map here? So you take any point in the Teichmüller space of S. Okay, so I'm thinking of this now as a conjugacy class of representations. Okay, you choose any representative in here, call it rho, and then you post-compose this guy with this irreducible one. Okay, so now this guy is a map, is a representation from gamma to PSL2R and then to PSLV. Okay, and then you take the conjugacy class inside of here. Alright, so the fact is that this is a well-defined map, it doesn't depend on any of the choices I made. Okay, and with this you can define the Hitchin component. Okay, so the PSLV Hitchin component, which for the rest of today I'll denote by HitVS. Okay, this is the connected component of this space here, which I'm going to denote by XVS. Okay, it's the connected component of this space that contains the image of I. Okay, so here I'm using the fact that the Teichmüller space of S is connected. Okay, in fact, it's known to be topologically a cell. Okay, so this is something that's connected, and the map I is continuous. Okay, so the image of this guy in here is also connected. So you can talk about the connected component of this space that contains this guy. Okay, another way to say this is the set of the Hitchin components, the set of points in here that you can continuously deform to a point in the image of I. Okay, so this is called the Fuchsian locus of the Hitchin component. Alright? So when V equals to R2, okay, then it is easy to see from these definitions, once you know the correct facts, that the PSLV Hitchin component, in this case, is just the Teichmüller space of S. Okay, so the fact you need is that the Teichmüller space is a connected component of its character variety. Okay, so you can think of the Hitchin component as a generalization of the Teichmüller space to the setting when my target D group is something more general. It's not PSL2R, it's PSLV. Okay? Now the first general result proven about the PSLV Hitchin component is a theorem by Nigel Hitchin, who used the Higgs bundle techniques to show that the PSLV Hitchin component is real analytically diffeomorphic to R to the n squared minus 1 times 2g minus 2. Okay? So in general, if you look at XVS, this is a real analytic variety. Okay, so you might have some singular points, but this is saying that the Hitchin component, right, this subset of this variety does not have any singular points. It's a smooth manifold. Okay? Furthermore, I mean, the topology is very simple. Okay, it's just a cell. So this generalizes the well-known fact that the Teichmüller space is a cell of dimension 6g minus 6. Okay, but this theorem here doesn't really tell you much about the properties of the representation in the Hitchin component. Okay, one reason people care about the Teichmüller space so much is because they know a lot about the geometric properties of the representations in here, in the Teichmüller space, right? They all are discrete faithful, they act properly discontinuously on H2 and so on. Okay, so this was a problem until François Laborie came along, and he proved that every PSLV Hitchin representation, right? That's a point in the Hitchin component, is what we today call a Nosov. Okay, so I'm not going to spend much time saying what Nosovness means, but you should think of this as as a condition that ensures that your representations all have good geometric properties. Okay, just like the representation in Teichmüller space. So in particular, this Nosov property ensures that every single PSLV Hitchin representation is a quasi-isometric embedding from gamma equipped with any word metric into PSLV equipped with any left interior metric. Okay, so more informally, this is saying that for every PSLV Hitchin representation, right, the way that it takes gamma and puts it inside of PSLV preserves the coarse intrinsic geometry of gamma. Okay? So this is the PSLV Hitchin component. Okay, so to summarize, this is a connected component of your character variety that consists only of smooth points, and every representation in there have very good geometric properties. Okay, so this is the space that we would like to study. Okay, so next I need to tell you what is the second thing in my title. What is the Goldman symplectic form? Okay, so this is a symplectic form that you can define in a pretty general setting. You can define this on the set of smooth points of any character variety of representations from a closed surface group to a reductive Lie group. Okay, but for today I'm just going to define this for the Hitchin component. Okay, so to define this you need two observations by Bill Goldman. And the first is the following. Okay, you look at the tangent space to the Hitchin component at any point in the Hitchin component. Okay? This guy is canonically isomorphic to the first cohomology of your surface with coefficients in the SLV bundle over the surface twisted by n rho. Okay, so let me explain a little bit what this means. So here, SLV is the Lie algebra of the Lie group PSLV. Okay, and you can think of this as the set of traceless endomorphisms or traceless linear maps from V to itself. Okay, you take any linear map, you choose any basis, you write down the associated matrix, and you require the trace to be 0. Okay? And then this bundle here, right, is defined to be the product of the universal cover of the surface times this vector space, and I quotient the entire thing on my gamma. Okay, where gamma here acts on the universal cover by deck transformations, and on this vector space SLV by n rho. Okay, by this n rho. Right, because rho takes gamma into the Lie group PSLV, and the adjoint representation takes PSLV into the endomorphisms of its Lie algebra. Okay, so you can. So this is what this bundle is. And so here you take the first cohomology of the surface with coefficients in this flat bundle. Okay, so if you're not familiar with cohomology with coefficients in some weird bundle, okay, for today's talk it doesn't matter. The point is the tangent space with the Hitchin component, right, can be canonically identified with some vector space that arises from some cohomological construction. Okay? So that's the first observation that Goldman made. The second observation is the following. Okay, first you consider this bilinear pairing B on the Lie algebra of SLT. Okay, so it takes two elements. This guy is naturally a vector space, right? You can add and traceless endomorphisms to get another one. You can scale them by new numbers to get another one. Okay, so I take two elements in the vector space and then give you a real number. Okay, and the way I'm going to do it is the following. Okay, I take any two of these guys, I compose them, and then I take the trace of the composition. So each of these guys are traceless, but the composition is not, might not be. Okay, so you can take its trace. Okay, so this turns out to be a bilinear, symmetric, non-degenerate form that is invariant under the adjoint action of PSLV on SLV. Okay, so for those people who are familiar, this is basically a scalar multiple of the killing form on this semi-simple Lie algebra. Right? So it has all the properties that I mentioned. Okay, so using this, you can construct another bilinear pairing, but this time on the first cohomology of the surface with coefficients in this flat bundle. Okay, so the way you define this bilinear pairing is a two-step process. First, you send this to the second cohomology of your surface with coefficients in R. Okay, and the way you do this is the following. Okay, so when I give you two cohomology classes in each one, right, the kind of usual way to combine them to get a second cohomology class is to use the cup product. Okay, but if you just use the cup product, then it doesn't combine the coefficients correctly. Because if you just apply the cup product to two first cohomology classes in here, you're going to get a second cohomology class with coefficients in SLV at rho tensor SLV at rho. Okay, but I want to get coefficients in R, so I use this bilinear pairing B to pair the coefficients. Okay, so that's what this symbol denotes, and you get something in here. Okay, and then now you can take the cap product with the fundamental class of the surface. Right, remember S was closed and oriented, so there is a canonical homology class H2SR, the second homology class. And so you take the second homology class to get this way, pair with this second homology class to get something in the reals. Okay, so this is a bilinear pairing that is skew symmetric. The observation of Goldman is that this guy here is a symplectic form on the Hitchin component. Okay, the symplectic form here just means that this bilinear pairing is non-degenerate, skew symmetric, and if you think of this as a two form on the Hitchin component, okay, by this identification, right? So at every tangent space, you think of the tangent space like this, and you construct this two-form, this bilinear pairing, this two-form is a closed two-form on the entire manifold, Hitchin component. Okay, so that's what Goldman proved. Okay, so in the case when V equals to R2 again, so when V equals to R2, okay, so then omega, this Goldman symplectic form, is a multiple of the Weil-Petersson symplectic form. On the Teichmüller space of S. Right, so remember when V equals to R2, the Hitchin component is just Teichmüller space. And this Goldman symplectic form is essentially a very classically studied symplectic form. Okay? And so the question that I'd like to address today is what does omega look like? On the PSLV Hitchin component. Okay? So this is a very vague question, but fortunately there's a model answer given to us by Wolpert in the setting of Teichmüller space. Okay, so what Scott Wolpert says, well, he was working in Teichmüller space. Okay, so I'm going to suppose that V equals to R2. Then what Wolpert says is that for any Pence decomposition, shall denoted by curly P on S. Okay, so this is a maximal collection of pairwise non-intersecting simple closed curves on the surface, right? So it's a way to cut your surface into distinct pairs of pens, like thrice-punctured, three-hole spheres. Okay, for any Pence decomposition P on S, the Fenton-Newton coordinates on Teichmüller space associated to the Pence decomposition, right, is a global double coordinate system. On the Teichmüller space, for omega, I guess, for the Weil-Petersson symplectic form. Okay, so what do I mean by a global double coordinate system? Okay, this means that you can write the symplectic form as the sum over all the simple closed curves in your Pence decomposition of the Li wedge theta I, where Li and theta I are the Fenton-Newton length and twist coordinates associated to the simple closed curve in P. Okay. So the point here is whenever you have a Pence decomposition, you choose a Pence decomposition on the surface. This determines a natural coordinate system for you. Okay, this is on the Teichmüller space of S, where the coordinate functions are Li and theta I varying over from 1 to 3g minus 3, and these can be described very explicitly. Okay, using the hyperbolic structure of the surface. So you take the Li and the theta I, this gives you two one forms, and you wedge them together, that gives you a two form. And that two form is exactly the Weil-Petersson symplectic form. Okay? So this is a very concrete description of what the Weil-Petersson symplectic form is, right? If you're willing to choose some topological data on your surface. All right? So this story has been generalized to the case. So this is partially generalized. To the case when the dimension of V is 3 by Hong Chang Kim. This was done in the mid-90s. And the case when n equals to 4 by Hong Tengren Zhang. Again, this is very recent work. I don't think it's on the archive yet. Okay, and the main tool they use here is this technique known as Fox calculus. Okay, and this is a technique that Goldman actually introduced in his original paper where he talked about the Goldman symplectic form. And as a procedure to algorithmically compute what this symplectic pairing is at every smooth point of the character variety. Okay. However, this procedure has a drawback, right? Which is that the computation you need to do here gets really complicated really fast. Okay, so even in the case where n equals to 3, if you look at Hong Chang Kim's paper, it comes with attached to this mathematical file, this huge mathematical code, right? That you need to rely on in order to for his theorem. And say in the case where n equals, and I guess the same will be true for Hong Tech's result. In the case where n equals to 5, nobody knows how to use this kind of calculation, right, to prove an analog of Wolpert's theorem. Okay. So, so I guess next I would like to talk about my results that I proved with Jesun and Anabi, right, about generalizing this theorem to the case of Hitchin representations. Okay. So,
so is it easy to say what is it that they prove?
What is
the result?
Yes. So, in the case when so let me just talk about Hong Chang Kim's result, right?
Sure.
Yeah. And for Hong Tech, I'm not really sure what is the full. So in the case of the SL3R Hitchin component, right? The PSL3R, what Goldman did was he actually, he actually coordinatized the space, right? In a way that's very similar to the Fenton-Newton coordinates, right? You cut your surface into pairs of pairs. For each pairs curve, you specify 2 length parameters and 2 twist parameters. And for each pair of pairs, you specify 2 parameters that determine the structure on the pair of pairs once you fix the eigenvalue data polynomial on boundary. Okay? And what Hong Chang Kim did was he showed that if you look, he computed all the simplex. So these are functions on the Hitchin component, and you can compute the Poisson pairing of these functions corresponding to the symplectic form. And what Hong Chang Kim did was he computed the pairings between the lengths, the twist and lengths, and the 2 parameters associated with a pair of pairs. Okay, but he did not compute the pairing between the 2 parameters associated with a pair of pairs and the length and twist. Okay, that was the step that was missing from what he did there. All right.
Is his formula correct then?
For the stuff that he wrote down is correct.
Okay.
Modulo the mathematical computation, which I did not verify.
Yeah.
He uses mathematical in an important way for his.
Yeah, but can you see that his result is the same as your result?
It's different. I can see that it's different. I mean,
You can see that it's different.
I can see because I did not say what my result is yet. But he did not compute the pairing, the Poisson pairings between the functions associated with the pair of pairs and the functions associated with the curves. Okay, he did not compute those. So that's why I say partially generalized. And I think in the n equals to 4 case, Tengren Zhang has some way to fix in the n equals to 3 case, but I'm not really sure what it was.
But it sounds, when you say you can see it's different, it sounds like you're saying that his thing is false. Right?
I can see it's different, but I don't know whether what he says is false. But I think there's a gap in it. There's a gap in. There's a piece missing to get a full Wolpert's theorem. Okay, you have to do that computation somehow.
So his work is he computes Poisson brackets between these,
between these
but
functions.
not all of them.
No, yeah, some subsets of them.
Okay.
Okay. Okay. So just like Wolpert's theorem, right? In order to state his result, he needs to make some topological choice on the surface, which is the Pence decomposition. Okay, so I need to in order to state my results, I need to tell you how to make some topological choices on my surface. Okay, so these are the topological choices. Let T be an ideal triangulation. On S, and then I'm going to let J be a compatible bridge system. Okay, so I'm going to tell you what these 2 objects are. but I would like to first emphasize that these are purely topological. Okay, once I specify the fundamental group of my surface, I can use that to tell you what these two objects are. However, if you choose a hyperbolic metric on your surface, then these two objects become realized as geometric objects on your surface. Okay, and today I'm going to, in the interest of time, I'm just going to tell you what their geometric realization is. Okay, so I'm going to choose a hyperbolic metric. Sigma of S. Okay, so sigma is just the surface S equipped with a hyperbolic metric. Okay, then an ideal triangulation of your surface is a way to cut your surface, your hyperbolic surface, into hyperbolic ideal triangles using finitely many simple geodesics. Okay, so when you look at the ideal triangulation on a surface, right? Because I have this requirement that I only use finitely many geodesics, you necessarily have to have some closed geodesics. Okay, so you're going to have some closed geodesics. You have to use some closed geodesics that look something like this. Okay, and then, okay, but of course this does not cut your surface into ideal triangles, right? So you need to throw in more things. And the other things you throw in are not closed geodesics, but they kind of spiral onto these closed geodesics. Okay, so it looks something like this. Okay, on this side, something like this. Okay, so I've drawn one of these. So these are called isolated edges, the red ones. Isolated. No, sorry. These are called the closed edges of your ideal triangulation. And the yellow thing is called an isolated edge of the ideal triangulation. Okay, and you need to keep throwing in these yellow things until you cannot anymore, right? You're only allowed to put them in a way that doesn't intersect the curves that are already there. And you keep throwing in until you cannot anymore, and that cuts your surface into a bunch of ideal triangles. Okay, so maybe this is easier to see in the universal curve. So here, this is a picture of the universal curve of sigma. So this is sigma. Okay, which is isometric to the Poincare disk. Okay, now if you take your closed edges and you lift it to the universal cover, you're going to see infinitely many of the lifts, right? I'm just going to draw two of them. Okay, you can see these two guys. Okay, so these are the lifts of the closed edges, and then you're going to see the lifts of the isolated edges, right? They kind of accumulate onto the lifts of the closed edges. So you can see a picture that looks like this. Okay. Then you have more on this side. You're going to have a picture of it. There are infinitely many of these triangles, and they all accumulate onto the red stuff. Okay, and each of these are these ideal, hyperbolic ideal triangles, which if you look at the covering map, maps injectively onto your surface. Okay, so this is what the picture looks like in the universal cover. Oh, two colors only. Okay, well, me too. So, okay, so that is what T is. Is there another color?
Maybe in
Oh,
that
yeah. Yeah, that's great. Okay, so I've explained to you what T is. Now, what is J? What is a compatible bridge system? Right, so downstairs, you can think of this as simply a choice of a short transverse arc across each closed edge. Okay, so if you lift this to the universal cover, what you're going to see is a gamma invariant, right, under deck transformations, a choice of these short transverse arcs across the closed edges. Okay, and really what these short transverse arcs are doing is they're picking out, in a gamma invariant way, a pair of triangles across every closed edge, so that each of these triangles share a common vertex with the closed edge. Okay, so for example, this bridge here picks out these two ideal triangles, and they both share a common vertex with the red closed edge here. If you look at this side, this bridge here picks out these two ideal triangles, and this guy shares this common vertex with the closed edge, and this guy here shares this common vertex with the closed edge. Okay, so this is what a bridge system is. Okay, is this topological data. Okay, so with this I can state my first theorem. theorem 1 is, okay, so let T and J be any choice of a ideal triangulation and a compatible bridge system, okay? Then this determines a symplectic trivialization of the tangent bundle to the Hitchin component. Okay, in other words, there exists a symplectic vector space which I'll denote by WT, okay, and a symplectic bundle isomorphism which I'll denote by C of Tj, okay, from the tangent bundle of the Hitchin component to the product of the Hitchin component and my symplectic vector space WT. Okay? Where both of these are thought of as symplectic vector bundles over the Hitchin component. Okay? So this guy here is a vector bundle over the Hitchin component with fibers WT, and the fibers naturally have a symplectic structure. Right? So this is a symplectic vector bundle. Here, the tangent bundle of the Hitchin component has a natural symplectic structure coming from the Goldman symplectic form. Okay? So I should point out that this theorem is not just an existence theorem. Right? Everything here can be constructed explicitly. Okay? I can tell you exactly what is WT, and I can tell you what this map CTJ is coordinate-wise. Okay? So everything is very explicit, but I will not give you the formulas, right, to do that. Yeah, in the interest of time. Okay, but in any case, with this theorem, it makes sense to talk about the next definition. So a Tj parallel vector field okay, is on the Hitchin component is a vector field, is one, and is parallel with respect to the flat connection on the tangent bundle to the Hitchin component induced by this symplectic trivialization CTJ. Okay, so what am I really saying here? So on the right hand side, okay, you can look at the section, the constant sections of this bundle map, this quotient, right? Which basically you assign to every point. I mean, your section is a map from here to here, and you basically assign to every point down here the constant vector. Okay, so you have a bunch of vector fields here, and if you look at what these vector fields here under this isomorphism, right, then you get what we call the Tj parallel vector fields. Okay. So the next theorem I'd like to talk about explicitly describes what these Tj parallel vector fields are in terms of a real-analytic parametrization of the Hitchin component. Okay, so in order to tell you about that, I need to talk about the Walker-Bonner-Horn triad. Okay, Bonner-Horn. And very briefly, what they prove is the following. Okay, so again, their parametrization depends on the choice of T and J. Okay, so I'm going to let K be the number of closed edges of your ideal triangulation T. Okay, so I want to define the parametrization. I first choose an ideal triangulation and a compatible bridge system, and then I count the number of red edges, right, of my ideal triangulation, that's K. Right? Then what they say, what they prove is that there exists a convex polytope which I denote by PT, inside of R to the n square minus 1 times 2g minus 2 plus k times n minus 1. Okay, I'm going to denote this vector space by U for short. Okay, there is a convex polytope in here and a real analytic diffeomorphism. Okay, which I'll denote by phi of Tj from the Hitchin component to this convex polytope. Okay. So remember, the theorem of Hitchin was that the Hitchin component was dimension n squared minus 1 times 2g minus 2. So this complex polytope necessarily has to be of the same dimension. Okay, so this complex polytope inside of this vector space is of co-dimension k times n minus 1. Okay, so in other words, this guy here, this complex polytope Pt is cut out by k times n minus 1 linear equations and a bunch of other linear inequalities. Okay, that's what a complex polytope is. Okay, so what Bornholm did is they explicitly state what is this convex polytope. They give you the linear equalities and inequalities that define it. And they tell you what, they give you a realistic diffeomorphism like this, coordinate-wise. Okay? So everything here is very explicit as well. And then, so what can you, okay, so using this, you can modify this parameterization phi Tj, okay, to get another real analytic diffeomorphism, omega Tj, okay, from the Hitchin component to the same convex polytope. Okay, so here I'm giving you another parameterization of the Hitchin component by the same convex polytope. Okay, but the parameterization map is different. Again, the reason I want to change phi Tj to omega Tj is so that the following theorem is true. Okay, so theorem 2, let Wt inside of U. So remember U is R to the n squared minus 1 plus times 2g minus 2 plus k times n minus 1. So let Wt in here be the n squared minus 1 times 2g minus 2 dimensional vector space, the subspace containing Pt. Okay, the convex polytope. In other words, remember I said that the convex polytope was cut out by k times n minus 1 linear equations and a bunch of linear inequalities, right? I forget about the linear inequalities. These k times n minus 1 linear equations give me a vector subspace, and that is what Wt is. Okay, so it's the minimal dimensional subspace in U that contains Pt. Okay, then the map.
So why, yeah, so why didn't you, so the thing you called U, what is the point of U? Why didn't you call the Wt U?
Right, because okay, so there's a reason, because the parameterization they give, right? They give the fact what they did is they describe a map into this space. Okay, and they found too much, and this space has too many dimensions, right? So they found, I mean, they give so they give explicit functions of the Hitchin component, n squared minus this number of functions to this space, but of course the dimension is wrong, right? So what they found is linear relations between these parameters. Okay, that's why I stated it like that. Okay, the functions that they use are explicit, and that's what is really important. Okay. So the second theorem is that the map from the vector space Wt, this vector space Wt to the set of Tj parallel flows. Okay, so a Tj parallel flow is an integral flow of one of those Tj parallel vector fields that I defined previously. Okay, so now I'm going to define for you a map from this vector space to this space of flows. Okay, in the following way. You take any vector in here. Okay, I want to use this vector to define a flow. Okay, so what do I need to do to define a flow? I need to say if I pick any point in the Hitchin component and any time parameter, I need to give you a new point in the Hitchin component. Okay, so how do I do that? Well, first I use omega tj to send rho into my convex polytope. Right? So omega tj takes rho into here. Okay, then I'm going to add t times mu. Okay, so notice that this guy here, for sufficiently small t, this guy here lies in the convex polytope. Okay, you might not be able to do this for big t, but for sufficiently small t it does. And so since this guy lies in the convex polytope, you can apply the inverse map to get it back in the Hitchin component. Okay, so this is my flow. Right, and the theorem is that this map here is a linear bijection. Okay, so the set of Tj parallel flows has a natural linear structure. Right, if you take any two Tj parallel vector fields and you add them, you get another Tj parallel vector field. You take a Tj parallel vector field and you scale it by a real number, you get another one. Okay, so this is natural. So these are both linear spaces. So it makes sense to say this is a linear map, linear bijection. So the content of this theorem is that whenever I give you a vector in Wt and I construct a flow like this is in fact one of the Tj parallel vector fields that I define. And also every Tj parallel flow is realized this way. Okay? Yeah, so because this parametrization is explicit, right? This gives you a very explicit description of what all the Tj parallel vector flows are, vector fields are, and all the Tj parallel flows are.
So can I ask you?
Yep.
So I think I see another way to get a map like this. So I can take so if you have something in what's it, Wt, it defines for you like a constant vector field, right, on Hitchin times Wt.
Yes. Yes.
So that's a parallel vector field.
Yes.
And then by definition, so if you pull back the parallel vector field by that
Yes.
map here, psi bar,
Yes.
that's a parallel vector.
Yes.
That's a
Tj parallel
that's a
vector.
Tj parallel.
That's exactly the content of this theorem, right?
That's
That
the
this
same
Wt is the same as, I mean, when you do that,
you get the same.
you get exactly this. It can be described this way. Okay. So this Wt here is the same as this Wt here, except here I must specify a symplectic structure, right? This theorem doesn't involve any symplectic structure at all. Okay.
What was it again about theta that didn't allow you to do this, where you can with omega?
Theta? Oh, you mean phi here?
Oh, sorry, phi.
Yeah.
Phi, yeah.
Yeah. So I mean, okay. So for me to explain that, you need to know what these. I did not tell you what these maps are, so it's kind of hard for me to explain.
Okay.
But in short, right, basically, you know, in part of this parameterization, I kind of erase the picture, right? You have these closed edges, and some of the parameters you use kind of describe how you glue these surfaces together along the closed edges. And basically, the only things we change is the way they define the gluing maps, because initially we tried to prove this theorem using phi tj, and we kept running into the problems that we could not compute the symplectic pairings between the vector. Yeah, okay, so the issue is we couldn't do it for this parametrization because the way they defined, the way you glue the representations along closed edges, right? It was not, the way they defined it was not suitable for our computations. Okay, so we just changed the way they defined it. Okay, but you get another equivalently good parameterization, which works for the theorem. Okay. Okay, so with theorem 1 and theorem 2, combining these two, you can actually say quite a bit about the symplectic structure of the Hitchin component. Okay, so these are some corollaries. So first, you can say that every Tj parallel vector field is Hamiltonian. Okay, so theorem 1 tells you that every Tj parallel vector field is symplectic. If you look at the integral flows of these guys, they preserve the symplectic structure. Okay, and then if you combine it with theorem 2, I mean, all you really need about from theorem 2 is the fact that any two Tj parallel vector fields commute. Okay, but once you have that, then you can use that to prove that they're all Hamiltonian. Okay, and then using also combining these two, you can prove the following. Okay, for any times decomposition, P S. Okay, you can construct a global double coordinate system. For the PSLV Hitchin component. Okay, and also when V equals to R2, okay, this recovers the tangent-Nielsen coordinates. Okay, so this generalizes Wolpert's theorem to the setting of Hitchin components. Okay, and the way we give this global double coordinate system is also very explicit, as explicit as the tangent-Nielsen coordinates. Okay, so using this, you can say a lot of things now. Right? In particular, this implies that the Hitchin component equipped with the Goldman symplectic form is a complete integrable system. Okay, you can explicitly describe Lagrangian submanifolds of this thing. And also you can see that the function locus inside of here is actually a symplectic submanifold. Okay? So, yeah.
So what's the relation between the Pence decomposition and the pair Tj?
Right. So once you have a Pence decomposition, there's a way you can construct an ideal triangulation formula. Okay, which is well, I don't know, because you have two ideal triangles and you want to glue them together to get a thrice punctured sphere. There is one very obvious way to do it. Okay, so you do that, and then for J, there's kind of a canonical choice you can make from the Pence decomposition. Well, not canonical. There's some choice you can make. Okay, it's just like in the case of Teichmüller space, right? You can choose. You can choose the choice of J by basically kind of requiring your segment to be invariant under a certain kind of reflection. Okay, but if you make that choice, then you can get this this theorem from this thing. Okay. Okay, so 10 minutes left. All right, so let me, I probably won't have time to talk much about the proof, but maybe I can say a little bit about kind of the engine behind the proof. What is the geometric input that allows you to study these Hitchin representations? Okay, so this is a theorem of François Laboudi, obtained by combining the work of François Laboudi and Olivier Bichat. Okay, and what they say is the following. When the Hitchin component, let me write it on this last board. Is canonically in bijection with the set of Fourier curves C from the boundary of group to the space of complete flags, okay, that are rho equivalent for some representation rho from gamma to PSLV. Okay, I consider this space of curves up to projective transformations. Okay, And this naturally sits inside of the set of Fourier curves. See, from the circle to the space of flags, consider up to projective transformations. Okay, so let me explain. There's a lot going on here. Okay, so first, what is a flag? A flag is a nested sequence of subspaces, okay, one of each dimension, inside of V. Okay, so it's a nested sequence of. So Fi is an I-dimensional subspace. Just kind of stack them all up, put them inside of V. Okay, and so the space of all such objects is called the space of flags. Okay, so what is a Fourier curve? So here I'm looking at maps from the circle into the space of flags. Okay, I'm not going to define this formally, but you should think of this as requiring your map to have very strong transisality and continuity properties, as strong as you can possibly have. Okay, so this is the set of Fourier curves. Now what is going on up here? So remember, gamma was my surface group. Okay, it's the fundamental group of a closed oriented surface of genus at least 2, and that is known to be Gromov hyperbolic. Okay, so you can take this Gromov boundary, which is what partial gamma denotes, and this is known to be topologically a circle. Okay, so it makes sense to require a map from this topological circle to the space of flags to be Fourier. Okay, having maximal transisality and continuity properties. Okay, but the advantage of using the boundary of gamma here instead of S1 is that there's a natural gamma action on the boundary. Okay, so and of course you have PSLV action on the space of flags by projective transformations. So it makes sense to require this map to be rho equivalent with respect to some representation. Okay, and so what Labrie and Guichard say is that basically instead of thinking of the Hitchin component as a space of representations, you can think of them as a space of curves satisfying some gamma invariance property. Okay, sufficiently transverse and continuous curves satisfying some gamma invariance properties. Okay, and maybe in a few seconds, let me kind of tell you in broad strokes what you need to do. Okay, so first you need to give, the way we do it is we gave a geometric description of these TJ parallel flows. Okay, and the way we do it is first you define flows on this space. Okay, you define a family of flows associated to, in the following way. Whenever first you pick a triple of points on the circle, and for that triple of points, I specify a particular kind of flow on the space of Fourier curves. And also, for any pair of points on the circle, I define a particular kind of flows on the space of Fourier curves. Okay, the pair of points one in the case of RP1, you can think of it as a shear. Okay. However, this what you really want is a flow here, right? But then you can see that even if you start with a Fourier curve with some rho equivariance, okay, if you try to apply the flows that we define here, you're going to break the rho equivariance you have. So the idea now is you choose an ideal triangulation, and then you use the triangles and the edges of the ideal triangulation to define to specify the flows. Okay, so you take any triangle. For that triangle, it gives you a triple of points on the circle, and you can use that to define a flow. For any pair of points, for any edge of the ideal triangulation, it gives you a pair of points in the circle. You can use that to define a flow. Okay, and then you need to compose these flows in a way that makes it equivariant. Okay, but the problem here is now I need to compose infinitely many of these things, right? Because the gamma orbit of any triangle, any edge is infinite. And generically, when you do that,
Why do you need to compose the flows?
So okay, so for example, if I take a triangle, right, a particular triangle, I perform a flow associated with this triangle, it's going to break the rho equivalence. So what you do is you take that triangle, you look at its entire gamma orbit, and you perform the same flow to each of the triangles to maintain the gamma in the group action. Okay, but when you do that, you're composing infinitely many of these flows, which generically do not converge in any reasonable way. Okay, but what happens is that the choice of the bridge system is what allows you to make sense of this. Okay, and then basically you can make sense of this infinite composition, and you get a well-defined flow on the Hitchin component. Okay, and since these flows are described using this Fourier curve, right, which is really how this parametrization goes as well, the monohorn triangle one, it basically tells us how we should reparametrize the parametrization to get this theorem, theorem 2. Okay? And then, of course, you need to relate that to the symplectic structure of the Hitchin component. But that's another long story. Okay, which we basically need to figure out a way, given any two TJ parallel vector flows in this way, how do I compute the symplectic pairing between their vector fields explicitly? Okay, so that's another technique that we need to develop. Okay, so I think I should stop. Thanks.
Are there any questions for Tengren?
Maybe you said it already, but what does this map look like, this PT, the map?
Yeah, so the way that they define this map is they also use this Labrie-Guichard theorem. And so you have these curves, right? You basically think of every Hitchin representation of these curves. And then now, whenever you have a curve in the space of flex, you can use certain, you can define certain projective invariants associated with this curve. So for example, if you have a curve in RP2, for example, right? So for example, if you have a curve inside of RP2 that is sufficiently transverse and continuous. Okay, and let's say you pick a triple of points on this curve, then you're gonna have okay, so really this goes into RP2 times RP2 duo, okay, this picture, right, which is the space of flex into R3. Okay, so then if you take a triple of points on the circle, then for each point you send it to a point in RP2 and a point in RP2 duo, which is the tangent line. Okay, and you do that for 3 of them. Okay, and then this triple of flex up to projective transformation is a 1-parameter space. Okay, and there's a invariant of this triple of flex known as the triple ratio. Okay, you use that. And then there's other invariant that's called the cross ratio, and you can use that as well for the edges. And basically combining all these invariants together, you can get the coordinate functions of this parametrization. Okay, so it's built up of triple ratios and cross ratios, basically.
I had a question about theorem 2. I understood that T was supposed to be small, but what else do you need? What other properties do you need for T?
So we can, we can explicitly say what T is.
Okay.
For given any rho and every mu, we can say explicitly for which T this is defined. Basically, you need to, and as long as this convex pointer is completely explicit, right? And if I give you a point in this pointer, and I give you a vector, I can say exactly which T I can do this for, so that you stay in the polytope.
Oh, okay.
Okay, so as long as you stay in the polytope, then you can invert this and you can define this map, right?
Okay.
And that's exactly when the flow is defined.
Do you know that the map, let's see, which map? I don't know if I want to ask this about the map omega, that it's not symplectomorphism?
Wait, the map omega?
Right.
So if you equip WT with the correct symplectic form, this is a symplectomorphism.
Oh.
But yeah, but that's in essence what theorem 1 and theorem 2 combined says.
Wait, with a constant symplectic form?
Yeah.
Oh, but I feel like that's stronger than theorem 1 and theorem 2, isn't it?
Yeah, I mean, yes. So that's true, right? This is no. Maybe you can deduce. I think you can deduce. I mean, this theorem 2 is basically saying that you have your vector space and you have your convex polytope in there, right? If you look at the constant vector field,
Yeah.
right, that is a Hamiltonian vector field, and you take any two of these constant vector fields, they commute, right?
Yes.
So that I think that would tell you that that you are basically symplectomorphic to an open set
Okay.
in WT with some constant symplectic structure, right? Some symplectic, some non-degenerate skew symmetric.
Yeah, I think you're probably right. I just need to write it down.
Yeah.
Yeah. Okay. Are there any other questions? All right, well, let us thank Tengren again.